This video is about the curved arrow notation, which you should already be familiar with because of your experience with resonance. This notation and the underlying implications is fundamental to understanding chemical reactions and to understanding the thinking in organic chemistry. In this video, we'll also highlight 4 basic moves from which essentially all organic chemistry mechanisms are comprised. If you understand and can use these moves, this will save you from countless hours of memorization and frustration. I realize this is a big claim, but it is true. To begin with, let's look at teaching model number 1. The reason why I show you this is I want to highlight the idea that the curved arrow shows the flow of electrons, not the movement of atoms. Therefore, the second reaction that's shown is not correct, as it's showing the flow of atoms. The first example, or the top line, is correct. One of the challenges in understanding the curved arrow notation reaction mechanisms is that you have to keep in mind octets, implicit hydrogens, and formal charges. Notice that in this ketone molecule, the terminal carbon is actually making 3 bonds to hydrogens. I'll just write them in here. We usually do not write them in. Mentally, hopefully you can appreciate that they're there. Therefore, the hydroxide is only grabbing one of the hydrogens, and the pair of electrons that are used to make a bond between the carbon and the hydrogen are now being deposited onto this terminal carbon. So over here in the product, I'm going to write the 2 hydrogens that never move, and I'm also going to write the lone pair of electrons that get deposited. It's not necessary to write these, but understand that they are there. Therefore, you would understand why this terminal carbon has a formal charge that is negative. This carbon is making 3 sigma bonds and has a lone pair of electrons. The other thing to keep in mind is the reactants overall. So you've got the ketone plus the over the arrow hydroxide. Overall, these guys have a negative formal charge. Therefore, our product should also have a negative formal charge. One of the products is not written, and this is, of course, H2O. Normally, it's not necessary to write that second product. We're usually just interested in looking at the organic product. If it's important to write the second product, I will ask you to do so. So let's look at these 4 basic moves. The first basic move is the nucleophile attacks the electrophile. Of course, nucleophile is that thing which is attracted or loving to something that's positively charged. And so it's helpful perhaps right here to write positive loving. And the electrophile is that thing which is negative loving. The thing that's negative loving will of course be something that's positively charged. And so in terms of this first example, here is our nuke and here is our electrophile. So simply the nucleophile, something that has a high electron density, is attracted and will make a new bond to something that has a low electron density. It could be that a nucleophile actually attacks a carbocation, in which case we only need one curved arrow. Or it could be, as in our example B, that the nucleophile, our water, is attacking something that is neutral. And therefore we're going to need 2 arrows, because otherwise there'd be too many bonds being made to this carbon right here. And so you can see initially a new bond is being made and a bond is being broken. Let's look at some examples for you to try. I encourage you to stop the video and see if you can predict the products of these 2 examples of a nucleophile attacking an electrophile. Okay, so in our first example, it looks rather complex, but all that's really happening is our hydroxide nucleophile is attacking. When you go to write out the product, I encourage you to write out, in a sense, first everything that is not changed. And so I'm going to write the product down here just because I have a little bit more space. The bulk of the benzene ring does not get changed. I still have my chlorine. This pi bond is still intact. The curved arrow is indicating that a pi bond is being moved to the right-hand side here. I still have my nitrogen group attached. I still have my oxygen with its negative charge. There's now, however, going to be a double bond between the carbon and the nitrogen, and this oxygen is now only making a single bond to the nitrogen, and it's gained an extra electron. Finally, we have the hydroxide, which has joined the ring. The nitrogen will still have its positive formal charge. So if I back up for a minute and look at the initial reactants, I see a negative charge right here, a positive charge, and a negative charge. In my final product, I also see a negative, positive, and negative. The formal charge is conserved. I take another quick look to make sure that I've accounted for all the bonds, and I think I have, so indeed this is our product, the nucleophile attacking an electrophile. Let's look at the next example. This is example B. Again, I'm going to write out most of the stuff that doesn't get changed. So I still have the benzene ring that's intact. These pi bonds do not get changed. There's going to be a new bond being made between either this carbon or this carbon with the sulfur. I'm going to pick the lower carbon, so there'll be a new bond being made to the sulfur. In terms of what's attached to the sulfur, I still have two double bonds to oxygens, and I also have this now single bond to an oxygen, and this oxygen will have picked up a formal charge. There is, of course, a new bond between a carbon and the sulfur. Now, one of the things to keep in mind here in terms of conservation of charge is that originally our reactants are neutral. I see this negative formal charge in my product. That alerts me that I must have a positive formal charge. And indeed, this carbon that used to be making a pi bond is now electron deficient. And so now we have neutrality, both a positive and a negative charge, in our product. This is our new product. The next example that we'll look at is the loss of a leaving group. Sometimes it'll be as simple as what we see is in example A. Sometimes the loss of a leaving group can be a bit more complex, like in example B. You might recognize example B, that structure there, as being the intermediate that we drew in the previous example. All that's really happening in this case is that the chloride is being lost. The rest of the original structure is being, in a sense, reformed before it got attacked by the hydroxide. So let's look at an example that you can practice with. So I encourage you to stop the video and see if you can anticipate what the product would be. Okay, so let's take a look. Again, we would expect that the benzene ring would be intact here. In fact, nothing changes in the benzene ring. I'll draw the first carbon, and then I know that because of this arrow right here, the bond between my substituent carbon and the oxygen gets broken. This oxygen will now have a negative formal charge. But I also can see that the bond to the sulfur, this double bond to the oxygen, double bond to the oxygen, and bond to the CH3 group gets unchanged. Now again, consider conservation of charge. My original molecule is neutral. My final product should overall be neutral. I know that there was a bond being broken between the carbon and the oxygen, and now this carbon is electron deficient because the electrons in that bond went to the oxygen. I have a carbocation. Overall, my product is neutral.